So let's discuss the topic Dirac's free particle solution and which is also known as plane wave solution. So here is the thing. So the wave function xi has four components and the Dirac equation is exactly a set of four first order linear partial differential equations. So this wave function has got four components and then the Dirac equation would be exactly four. We would get four first order linear partial differential equations. The plane wave solution of these component functions will have the form. So the plane wave solution of these component wave functions will have the form. So xi j of r comma t, where j is goes to 1 2 3 4. So these are the component wave functions which could be written as uj into e power I into k dot r minus omega t. So this is the uh, component wave function. Component wave function would have this form. So it is a it is a function of r and t. Here you can see k dot r minus omega t uj. Just like y is also a sine kx minus omega t. We have that is amplitude of oscillation, like that. I mean displacement from the, in the case of oscillations we have this kind of form. Y is also a sine omega t, or a sine kx minus omega t, where e power I theta could be written as cos theta plus I sine theta. So here has here sine is there, so which could be written in this form, e power I theta form. So this is also the same manner, just like this. So in the place of sine we are writing just like this, e power I theta sine wave function. Because of the sine function form we would have this, and kx minus omega t, like that. So next is where j is goes 1 2 3 and so on. Uj are numbers. So here uj is nothing but number, and xij of r comma t are eigen functions of energy and momentum operators values. So these xij j's are nothing but eigen functions of the operators, energy and momentum operators. That is we know the form hxi is equals to e xi, like that. So like that. So with eigenvalues e is equals to h cut omega. So if e operates on wave function xi, then we would get energy operator, like the Hamiltonian operator, we would get its eigenvalue as h cut omega. In the same manner, if momentum operator operates on these wave functions, we would have h cut k as the eigenvalue respectively. That is the form a xi is h xi is equals to e xi, like that. So where h is the operator and e is the corresponding eigenvalue. So next, after substitution we get, so next what we need to do is we would get these four equations, that is from this uh, c into alpha dot p plus beta mc square into psi is also e psi. So if we substitute, if we take this equation and in the place of alpha, if we take that 4 by 4 Dirac's matrices, and xi has xi 1 xi 2 xi 3 and xi 4, so there is mentioning that xi has four components. So these are the four components. So if we replace xi with these four components, and if we do in the place of alpha those, if we do those calculation, we would get these four equations. So how means this? So the c into alpha dot p plus beta mc square into psi is equals to e psi. So this is the equation. So in this equation we need to replace xi with this xi 1 xi 2 xi 3 xi 4, 4 by 1 matrix, and this in the place of p is nothing but P is a momentum vector, that is nothing but px I cap py j cap plus pz k cap, and alpha is nothing but alpha bar is nothing but alpha x I cap plus alpha phi j cap plus alpha z k cap, where alpha x, alpha y, alpha z are the Dirac's matrices. So here you can see, so alpha x, so Dirac's matrices have the form 0 sigma x 0, that is 0 sigma x 0, here 0 sigma y 0. So this 0, this 2 by 2 matrix, I mean this 1 0 0 minus 1 is nothing but sigma z. Here also 1 0 0 minus 1 is nothing but sigma z, and this is nothing but null matrix 0 0 0. So 0 sigma z 0, and this one I 0 0 this uh, I 0 0 minus I. So these are the 4 Dirac's matrices. Now we need to substitute these matrices in this formula. So here you can see that. So this is the substitute, after substitution we will get. So how means alpha dot p means, first of all we would have alpha x px, that is the matrix alpha x multiplied with px. So this matrix into px we would get 0 0 px 0 0 px 0, that means this matrix multiplied with a constant. So if a into 1 0 0 1, that is nothing but a 0 0 a, like that. So like that constant multiplying with a matrix. In the similar fashion, alpha y into py, so this alpha y matrix multiplied with py, so like that. So we would have this form. So here you can see what we would get after multiplication. So here and all px, here minus ipy plus ipy, like that. So this is the form, and here pz minus pz, pz minus pz, like that. And here we are having mc square minus mc square, like that. So if you do after multiplication, we would have this form. So c into alpha dot p, this entire thing is nothing but which is in this this is alpha dot p plus beta mc square, alpha dot, this is alpha dot p, and plus beta mc square, beta into mc square, this is beta into mc square matrix. So we have beta matrix 1 0 0, here and all 1 1, and here minus 1 minus 1. So into xi 1 xi 2 xi 3 xi 4 e xi. So this is the thing. Now in the next step, if we do calculations, we would have this form finally. So here if we see first element, first row, first column element, this is that. So here we would get 0, c into 0 0, here also 0, here also 0, so all of them 0, but what would remain is mc square. So hence we are having mc square as the first row, first column element. In the similar manner, if we look up for the second element, so here 0 is there, here also 0, here also 0, here also 0, all of them are 0. So we would have 0 first row, second column element. And next thing is first row, third column element. So c into 0 0, here also 0, and c into pz, that is cpz, and plus 0. So we would have cpz. In similar manner here c into px. So first row, fourth column element, this is first row, fourth column element. So c into px, we would have cpx, and here also c into py. So this c into alpha dot p, that is so we would have so c into alpha dot p, this c multiplied with this, we would have c minus c ipy. So overall we could take c as common, px minus ipy, and remaining for this element 0, this element 0. So these are all the first row elements. In the similar manner, if we go for second row, here 0 0 0, everything 0. So in the similar manner, if we go like this, if we go on calculating like this, we would have this matrix after calculations. C into alpha dot p, this is nothing but c into alpha dot p plus beta mc square calculated matrix into xi is equal to e xi. Now we need to multiply these both matrices. This is a 4 by 4 matrix and this is a 4 by 1 matrix as it has 4 rows and 1 column. So here now matrix, we need to do matrix multiplication. So as we can see, this is a 4 by 4 matrix and this is a 4 by 1 matrix. So after multiplication, so number of columns of this matrix is equals to number of rows. So this one would get eliminated. So what would remain is 4 by 1 matrix after multiplication, matrix multiplication. So this row elements multiplied with this column elements, corresponding column elements, and added together we will get this. So mc square into xi1, 0 into xi2 is 0, and cpz into xi3 is xi3, and c into px minus ipy into xi4 is this. So overall you have this, and this e into this matrix we would get after multiplication we would get this. So this in the similar manner here also 0 into xi1, we won't have xi1 here, mc square into xi2 and c into px plus ipy minus pz. So corresponding elements, so this second row elements multiplied with this column elements, this next third row elements multiplied with this column elements, we would have these equations, corresponding equations, and these are the equations which have been given here. So after substitution we have said, and already we know that xi1 could be written as u1. So here initially there is mentioning, so xi1 could be written as u1 into e power I k dot r minus omega t. So if we take this I into k dot r minus omega t aside, common for all, so if we keep that aside, we would have, so we are having u1 here. So e minus mc square into u1. How means, so this as this both of these matrices are, so this matrix are equal. So this is a 4 by 1 matrix, this is also a 4 by 1 matrix, corresponding elements must be equal. So this one equals to e xi1. So if we do calculations, if we keep this e here and if we send this element that side, so we would get e minus mc square into xi1. Xi1 is nothing but u1 into e power I k dot r minus omega t. So hence here we are having e minus mc square u1. Next thing is here we are having cpz into xi3. When this goes to that side, minus cpz into u3. So next c into px minus ipy. If this goes to that side, minus cpx c into px minus ipy. So like this. So in the similar manner, here also e minus mc square, if we do the similar calculation we would have these 4 equations. So this is the way how we used to get these equations. These equations being homogeneous will have non-trivial solution only if the determinant of the coefficients is 0. So these are homogeneous. Why means this is energy. Here also yeah, it has got the dimensions of energy mc square into e1. So this is the that wave function, and c into pz. So momentum multiplied with velocity, it also has got the dimensions of energy. So here also the same, momentum multiplied with velocity. So hence they are all homogeneous equations, and they would have non-trivial solution. Trivial means x equals to 0, y equals to 0, z equals to 0. So unimportant solutions. So if we want to get perfect solutions, so x is equals to some 1, y is equals to 2, like that, some important solutions, it is only possible if determinant of the coefficients is 0. So these are the coefficients. So for u1 e minus mc square, for u3 cpz, for u4 minus c into px minus ipy. These are the coefficients, and for u2 in this equation 0 is a coefficient, and here also the same, this is the coefficient for u2. For u1 it is 0, and this minus c into px plus ipy, that is a coefficient. So in the similar manner, if we take the coefficients and if we write in matrix form, you would have this. So here e minus mc square 0 minus cpz minus cpx minus py. So just as discussed in this equation. Next, in this coefficient of u1 0, so you can see here 0, and u2's coefficient e minus mc square, here e minus mc square, and u3's coefficient cpx minus plus ipy minus of cpx in ip, and you force coefficients cpz. So if we write all these coefficients in matrix form, and if you find the determinant of these coefficients, it has to be 0. So on solving this entire determinant, which is a huge one, huge calculations, so finally we would get this. After finding determinant, e square minus m square c power 4 minus c square p square whole square equals to 0. Determinant. This is in agreement with momentum energy relation for a free particle. So this is the energy momentum relation from the relativistic case. E is equals to total energy, that is to square root of p square c square plus m square c power 4. So from that we would get that relativistic energy equation. This is, so explicit solutions can be found for any momentum by using a sign for energy, say. So if you want to find different solutions, so this one equals to 0. So this one into the, if what does it mean if a minus b whole square equals to 0? That means nothing but a minus b into a minus b equals to 0. So that is nothing but a equals to b, a equals to b, 2 times like that. So if we do simplification, so this e square would be equal to p square c square plus m square c power 4. That is nothing but e is equals to square root of p square c square plus m square c power 4. So as we are getting square root, it would be plus or minus. So if we take plus square of the square root, so that is nothing but e plus energy. So plus of square root of p square c square plus m square c power 4 from here. So the determinant 3 is of rank 2. So this determinant is of rank 2, they are saying. So it is a rank 2 matrix, number of independent rows, columns. That is, to show this we replace it by delta. So this entire determinant is replaced with delta. So here you can see delta is the determinant. So how we used to find the determinant is, first e minus mc square. So eliminating, so e minus mc square. Now we need to eliminate its own column and row. So after elimination, what we would have, this e minus n, this 3 by 3 matrix, this. So that one you can find here. So that is the thing. So cpz 0, e plus mc square, cpz 0. In the similar manner, next minus. So here it is plus, next minus, next plus, next minus. So here already we have taken plus, so here minus 0 0 into this row, this column and this row must have this column and this row has to be eliminated. So after eliminating, you get this 3 by 3 matrix. So 0 into anything is 0, so we won't have that. Next minus cpz, so plus minus cpz into, after eliminating this column and this row, you would have this would remain. So that is the thing here. So in the similar manner for this also, minus cpx minus ipy. So if we do, we would have this. So plus minus plus minus. So actually we would have here a plus sign. So after the calculation, this is the way to find the determinant of this matrix, 4 by 4 matrix. So finally after calculations, we would have this. So this one into this one equals to 0. That is here just like a minus b into a minus b equals to 0. So we would have a is equals to b, a is equals to b 2 times. So like that, determinant is this. So each cofactor is 0 and so on. From 3 we obtain. So from this, after solving, we would get, so after sending this m square c power 4 c square d square, that's that, and taking its square roots, we would have this. That is, the relation between e and p is an agreement with Schrödinger picture. Hence we can assign numerical values to of use. So we choose terms conveniently and obtain linear independent solutions, taking first. So as we can assign numerical values to of use, and first we are taking plus or minus is there energy. So first if we take plus, So there are two linearly independent solutions which are conveniently written as. So as there are four equations, the solutions for these equations would be this, would better be this. So this is the one of the solution of the first equation, I mean out of the four equations. So if we substitute that u1 is equals to 1 and u2 equals to 0, u3 is equals to this in these equations. So this is slide 3. So actually, so slide 9. So here independent solutions is u1 is equals to 1 and u2 equals to 0. So how means, if you see here, so if we place in the place of u1 1 and u2 is not there, so that is 0. Next uh, in the place of u3, cpz by e plus mc square. So cpz, why need how it gets cpz means here already one cpz is there, so again cpz some and e plus in the denominator what we are having, so that is e plus mc square. So cpz into cpz, we would have c square pz square and e plus mc square. So uh, so that is the in the denominator. So similar manner here what we are having, minus c into px minus ipy. So u4 what we would be having is correspondingly c into px plus ipy by e plus mc square. So what happens is cpx plus ipy here in the place of u4. Here c minus c px minus ipy. So px minus ipy into px plus ipy, if we do, we will get px square plus py square, that is a minus b into a plus b, that is a square minus b square. So px square minus b square is nothing but ipy whole square, I square is nothing but minus 1, so minus into minus plus. So what we would have is here we are having minus c square pz square, here minus c square px square plus py square. So and in the denominator what we are having, e plus mc square. So if we take LCM, here 1 is there, so if we take LCM e plus mc square, if we take, so we would have so in the place of e, if we replace it with e plus, so in this equation, so what we would have a minus b into a plus b, that is a square minus b square. So we would have e square minus m square c power 4 in the numerator, and here minus c square pz square minus c square px square minus c square pz square, that is nothing but, in short, we could write it as minus c square p square. So already we know that e square minus m square c power 4 minus c square p square is equals to 0. So what would happen is the numerator would become 0, which is nothing but equals to 0. So that is nothing but the values of u1, u2, u3, u4. So which values? So these values of u1, u2, u3 and u4 would definitely satisfy this equation. So this is the, so nothing but the solution of this particular equation. In the similar manner, if you see for yourself, if you substitute these values for the second part of the equation, so u1 0, u2 1, so u1 not there, so it's 0, so u2 is 1, again we would have e minus mc square, similar manner, and u3 you could see that it is px minus ipy. So u3 is px minus ipy into c by e plus mc square, and u4 minus cpz, because here we are having plus cpz. So again if we do solvation, we would have this term in the denominator, so that is something sorry, this term in the numerator, so that is nothing but equal to 0, hence the equation would be satisfied. So these are the possible solutions. In the similar manner, similarly, if we choose negative square root, so if we take square root can be positive or negative, so in the next case we are choosing it to be negative. If we place this negative square root again, if previously we have taken e plus, now again e minus, So E minus MC square, like that. So here E plus MC square, here we are taking E minus MC square. So previously we have taken E plus MC square, but here we are taking E minus MC square. Why means here previously E minus MC square is there. So E plus MC square is nothing but A minus B into A plus B. But here in the next two equations we are having E plus MC square. E plus MC square. So hence we need E minus MC square in order to get A square minus B square. So hence for the remaining two equations we are having this E minus MC square, so that we could get A square minus B square. So only that thing changes here, minus sign changes, remaining all as usual. So U3 1, U4 0. So U3 1 as usual, and U4 not there. So U1 would be CPZ. U1 would be CPZ. So here CPZ is there, and U2 PX minus IPY. So U2 into Px minus IPy is there. So in the place of U2, Px plus IPy into C, like that we used. Okay. So these are the possible solutions satisfying the equation. So each of the solutions can be normalized by multiplying it with n in the sense. So we need to normalize these equations. That means the wave function xi. In order to normalize that wave function, we need to multiply it with the normalization constant n. So after multiplying, we would have in such a manner that xi star into xi must be equal to 1 in this manner. So with what is the normalization constant we need to multiply, so that we would have xi star into xi is equals to 1. So now we need to normalize this wave function. So xi star into xi. So xi star is nothing but transpose conjugate of xi. So this is xi. I mean, of course, e power I kx minus omega t is missing here. So if we keep that as it is common for all the things, so we can just take them aside. So if there is a matrix like Ka, Kb, Kc, Kd, so we could write it simply as K into A, B, C, D matrix, like that. So like that, if we just take out that e power I k dot r minus omega t, so this one would remain u1 into e power I k dot r minus omega t, u2 into e power I k dot r minus omega t, like that. So at a particular point and time, so we would have xi1, this one. So xi star is nothing but transpose conjugate. So if we do transpose, so here 4 rows and 1 column is there. So after taking transpose, rows would get converted in columns, or columns would get converted into rows. So this column would get converted into rows of this u1, u2, u3, u4 in a row form, and its conjugate would be u1 conjugate, u2 conjugate, u3, u4 conjugate. So without conjugation, we would have u1, u2, u3, u4, like that. If we take transpose of this matrix, and again applying conjugate, it would be like this. So now if we see here, this mode multiplied would give us 1. So this is 1 row, 4 column matrix, and this is 4 rows, that is 1 2 3 4 rows, 1 column matrix. So number of columns here and number of rows here are equal. So if we eliminate this 4 and this 4 here, we would have 1 by 1 matrix, that is an matrix of containing only one element. So if we see how it is, means u1 star into u1, so u1 star into u1 plus u2 star into u2 plus u3 star into u3 plus u4 star into u4. So corresponding elements in this matrix, if you multiply and add up, so that is nothing but matrix multiplication. So we would have this. So now as we have taken normalization constant, so in addition to here only 1 is there, But if you multiply it with normalization constant 1 into n, we would have n. 0 into n, 0 of course, and this u3 into n. So n into cpz e plus nc square, like that we need to multiply with n. So after doing that, what we do have is, so u1 into u1 star. If you see for this, u1 is 1 and u1 star is also 1, because there is no such thing like I. This is just a number, it's not a matrix. And here conjugate, if we as this is a real number, so like that. So u1 into u1 star is 1, so we would have 1. So hence we are having 1. u1 into u1 star, that is u1 into u1 star is nothing but 1. 1 into, of course, n square, n into n, that is nothing but n into 1, n square. And 0 into 0 is 0, like that. Of course we could take n square common. In the similar manner, u3 star into u3, so u3 is this, u3 star is also this only, because I not there. So you would have pz square c square n square, pz square c square into n square. N square would be taken common, and whatever is there in the denominator. And next, for u4, however, px plus ipy is there, I is there, the term. So conjugate of this would be px minus ipy into c by e plus mc square, that is the conjugate. So if we do multiply u4 into u4 star, that is px plus ipy into px minus ipy, that is px square plus py square, we would get n square. So px square plus py square into n square c square. And so in this manner, which is nothing but equal to 1. So this manner we would get after solvation. This is the thing we used to get. So next, what we need to see is, here 1 plus 0 is nothing but 1, and here c square pz square, here also c square is there. If we take c square, and numerator and denominator is also the same for both, so hence c square e plus mc square whole square. So px square py square pz square all added together. So next we need to send this one to this side. So this is, here it is multiply in the, so if it here it is multiplying, so if it goes to that side, it would get divided. So next thing is, we would write this px square plus py square plus z square has p square. So this is the thing. And on solvation, this is nothing but actually this is nothing but n square. If we want to find out n, just taking square root of this, that is nothing but 1 by square root of this term, so which could be written as this form: 1 plus c square p square plus e plus mc square whole square all to the power of minus half. So finally this is the normalization constant. So so the solutions are nothing but, these are the solutions, plane wave solutions. So this fourth equation and this fifth equation, these are the solutions, and this is the its corresponding normalization constant. So this is nothing but Dirac's plane wave solution. So thank you.